And I thought maybe I should just skip to this right now. This is a little bit technical, and I'll need to write stuff, and if I start too late, then I'll be rushing through it as usual, and it won't be so good. So if you don't mind, shall we skip to this right now? Forget about the case and stuff. Okay, so as I said, this model is a little bit different. It's a bit more involved than the 3D Denis-Diderot rotation. I'll be looking at a shallow water equation with rotation. So again, for those of you who were at Vin's talk this morning, we've seen that equation before. So I'll skip all the scalings and everything, which lead to the equation I'm going to write. So okay, I'll write down the equation and then I'll try to explain what's going on. So basically, eta will be a height fluctuation of the water. Okay. And I'm looking at u will be a velocity, velocity. But I'm assuming that I'm looking at my shallow water here, which is forced by some stationary forcing, whatever the wind. And I'm going to linearize the equation in some sense. Well, I'm going to assume that u, the velocity, is a perturbation of some stationary solution, which I'll call u bar. Okay. So I'll probably be making some assumptions on u bar as we go along. That's u bar. And so the equations in the end, once you've done all the scalings you want, are the following. And if you want to know exactly my scalings, I can tell you later on. So here's the model. I'm try to write it the right way. So dt eta plus divergence u over epsilon, where epsilon will be the fluid number, Rossby number, with some scalings, plus u bar eta. So just checking not doing things wrong. Okay, then I have a nonlinear term. So because of my scalings, so this is cheating, of course, but we sort of chose everything so that the nonlinear term is very small. So my problem will be basically linear, and then dtu plus gradient theta over epsilon, plus the rotation, which I'll choose to be a function, again b over epsilon squared, u perpendicular, just like before, plus the transport, plus a reaction term, plus a nonlinear term, which again is very small. Is equal to 0. So, of course, there are parameters here, okay? And I'm not telling you why this is the equation I come up with, but if you want, I can tell you what orders of magnitude we chose to get precisely this equation. I had that written down somewhere, but if you like, you just believe me that this is the equation I'm interested in, okay? B of x2 here, so I forgot to tell you before, and someone mentioned that when I was saying I have one theorem for a constant b and another one for a variable b, they weren't the same limiting systems, you probably noticed. One was a heat equation, one was 2D Denis-Diderot. And I forgot to tell you when b is variable, I was saying b is smaller than something positive. It's actually, its derivative is almost nowhere vanishing, of course. I thought you could have both theorems for the, okay. Anyway, so here I don't really care. Actually, I do care that b should go to infinity as x2 goes to infinity. So, of course, physically I'm doing the beta plane approximation near the equator. So you could imagine b of x2 is just x2. Okay, that's the beta plane approximation. And then I'm saying x2 is going to infinity, which physically is sort of not very physical, right? But what happens is that the waves associated with this equation here, with the linear part, are confined near the equator, as you probably know, and we can prove, right? They're just like Hermite functions. So basically going doesn't really make any, it's not really a problem to say x2 is going to infinity, in the sense that the solution will be a sum of Hermite functions which are sort of localized. So maybe in some way we could make sense to this. But anyway, it's very important for me to have this, and I have x2 in the whole space. So even if physically this is not good, this is really what I have to do. Okay. And I'm in 2D here. And so as before, the question is what happens when epsilon goes to 0, but actually the question is a little bit different in the sense that, okay, we came up with this model when we read part of the book of Pedlowski, where somewhere he was saying that you have lots of waves associated with the system. You have Poincaré waves, Janai waves, Rossby waves. And he was saying, somewhere in his book he says Rossby waves are trapped, right? And we didn't understand exactly what he meant, and we're trying to prove that that's the case. Okay? So what I want to do here is not really study the limit of this equation as epsilon goes to 0. I think for the time I have, this guy will just forget about nonlinear terms. I just want to look at the linear problem with this these transport terms, right? I want to show there are Rossby waves for in general B and Poincare waves, and I want to understand what a trapping of Rossby waves means, just for a linear problem. Again, with this scaling, the nonlinear solution will look very much like a linear solution anyway. Okay? So let's just look at the linear equation. And so the reason why we chose those scalings, okay, is that actually you can write it down a tiny bit differently as follows. Let me just look at a linear problem. Yeah.
Basically, B going to infinity is what makes the waves trapped.
Yeah, exactly. So since they're trapped, you can say it goes to infinity, since anyway they're trapped.
If there was anything left,
definitely.
Would blow off.
Definitely. I definitely need that. Okay, so linear problem. Just forget about the nonlinear terms for today. I'll just write it differently. I'll write it, so I'll call U, capital U will be eta small u. Okay, so 3 components here. So I can write it in the following way, and I'll try to analyze what I'm saying. So I have epsilon squared, just multiply everything by epsilon squared. Okay, and then here's what I have, something like that. Some operator, which depends on x because of u bar, because of b, for which every time I have a derivative, I have an epsilon in front of it. Okay, so you can check, if you multiply by epsilon squared, well, I'll define a in a second, you'll see there are epsilon derivatives everywhere. And I have, okay, plus some nonlinear term I want to forget about. Okay, so let me write this A. So it's a matrix. Okay, so what do I have on the diagonal? I just have the transport by u bar. So it's epsilon u bar, and then I said I had epsilon derivatives. Okay, so on the diagonal, I have this transport. Okay, and then, okay, I have some small mistakes due to the reaction term, which are very small. d1, u1, and then I have epsilon squared d2, u2. Okay. Now, here I have the term coming from the gradient, like an incompressible limit kind of term. And then missing 2 terms here and here, which are the rotations. So I have plus b, minus b here, b here. Okay, this is very badly written. Okay, and then I have, again, some term in epsilon squared, which I don't need anyway, so let's forget about it. Okay, so I have 3 columns here. This. On the diagonal, I have a transport, basically, up to epsilon squared. Here I have terms corresponding to the Froude number, like incompressible limit type of terms. And here, up to epsilon squared, I had the rotation. Okay, and I'm insisting on the fact, and this will be very important for me here today, that all derivatives have an epsilon in front of them. And that's why I'm going to explain a little bit about semi-classical analysis. Okay. So let's see, what do I want to say about semi-classical analysis? So, okay, so maybe I should talk a tiny bit first about microlocal analysis. So this is going to be very crude. So for anyone who knows about this, you're going to be shocked because this is going to be a very quick crash course in microlocal analysis. Okay, so please don't be mad at me. Just want to explain what this is all about. Okay? So microlocal analysis is a way of saying if I have an operator A, depending on x and d, I want to work with the operator. One way of working on it is replacing it. So that's the operator world, and this is a symbol world. By a symbol. What's a symbol? Well, you just take your A here and you replace it by A of x psi. You just replace, every time you see a derivative, you replace it by I psi. Okay, just an exercise. Game. For example, if I have x, it's x. If I have a derivative, it's I psi. Okay. If I have x times a derivative, then it's xi psi. But if I have a derivative applied to x times a function here, xf, then it's also I psi x. Okay, so that's important, is that the symbol does not see commutators in some sense. It doesn't see a difference between x derivative and derivative 2x. Right? It's the same symbol. Right? You have to think about that. Then that's right. And then, of course, if you have two operators and you want to take A applied to B, then you're going to have symbol A times symbol B plus all kinds of things. Okay. So the other way around, if I give you a symbol, can you make an operator? It's not so easy, right? Because here I have a symbol written the same. That's one symbol and two operators. You have to choose how to quantize your stuff. So just in that 1 second, if I give you a symbol and a number t between 0 and 1, A is my symbol here. Okay, so now it's small a, applied to a function u by definition. Okay, so I just write down the formula and then we'll discuss it, okay? So, okay, this is what you put, and then you put your symbol, and you choose how much weight you want to put on x and y. This is just a formula. Okay. What I want to check is that this formula does give operators I want. So t is anything between 0 and 1, and depending on what t is, you're going to get, for instance, for this symbol here, you're going to get either one or the other of the operators, depending on which choice of quantization you've used. Okay. So let's try. I mean, what should I do? I'll try x. Okay, so I stick x into this, and I want to find at the outside. I want to find x, right? Which is not totally obvious. Maybe if you see it's the formula, but actually it is, because if this is x, you're just integrating e to the I y minus x psi. So you're just having a direct mass in y equal to x, and since this was x, you get x u of x, whatever the quantization. If instead of this I'd put I psi for my symbol, if here I have I psi, then you see I psi is exactly a derivative in y of this phase here. Integrate by parts, you get dyu. Okay, then you integrate in y, x is equal to y, so that gives you dx ux. It's working. Okay, now what happens if I put I x psi? Okay. Let's see, if t is equal to 1, okay, then I have no y here. So if I replace the symbol by I psi x, x goes out, right? So I have x. And then my I psi I know gives me dx. Right? If I had t equal to 0, which means I only have the y dependence here, I would have dx of xu. Okay, so the choice of the way you quantify things is important. If I give you a symbol, the way you get the operator, I have to tell you my rules of quantifying. Usually, I mean, very often people will take t equal to 1/2, that way you don't really have to choose, right? It's halfway between one and the other. And this is what we call the while quantization, okay, which people use, I guess, more often. Anyway, so this is very useful because once you know how you quantize your symbols, then you have rules that tell you how you do operations between operators, right? Compositions, inverse, whatever. Okay? Now,
t and 1 minus t is the only way to get back, or are there other ways?
This is getting, I don't know. Okay. Maybe you can invent other, I mean, you can invent other ways, yes. This is classical, I guess, in some sense. But maybe you should actually follow them and know that more. This is a very classical thing you find in textbooks. That's the only thing I know. But okay, you see the big problem in some sense is the order of operations, right? Commutators are important and you don't really see them on the symbols. So that's where semi-classical analysis sort of helps you. So when you move on to semi-classical setting, the only difference is that instead of having derivatives, I have epsilon derivatives. It's the only difference, okay? So my operators look like this. Okay, no epsilons. Okay, but my symbols are the same. Okay, so epsilon d I replace by psi. Right? So you're not allowed to have d on its own, you're in big trouble, right? So always epsilon d. But what happens, so then you can play the same game, but what's interesting is that if you take the commutator now between x, epsilon d, and epsilon d x, for the function f, course what you get is epsilon f prime, right? Which means that it's small. So what you've gained when you're semi-classical is that you can really, I mean, quantization is easier in the sense that the mistakes you make when you do commutations and that kind of stuff, you gain a power of epsilon each time. Okay? So that's useful. Meaning that what's important when you're doing semi-classical analysis, in some sense, is what you call the principal symbol. Really, you take your operator, you replace all epsilon d's by xi's, and you really have not made much mistakes when you go back to your operator. Whatever quantization I use, whatever t here, the only mistake I will have made when I change t is of order epsilon. Because the mistake is just due to commutators. Okay? So the principal symbol really makes sense in this case, in this situation. Right? It's replacing epsilon d by psi, and then you can work on that, and any mistake you make will always be smaller than epsilon. Okay? This is crash course. Yeah.
But for this somehow you have to know that the f is not oscillating.
Exactly. So now, of course, I mean, this has no sense. If f, okay, if I'm saying I had epsilon derivatives, that means I'm in the special world, and not in the world of usual functions. So if I have a function f of x, and if I apply epsilon d to f of x, this is small, right? But if I have a function which is like this, right? Now epsilon d is order 1. Okay? So it's important when I live in a semi-classical regime to study functions which are oscillating. If not, I mean, everything is very small. I'm just working on some. Doesn't have much meaning, right? No sense. So, precisely, what does that mean? I don't want just to work with such functions. That's so interesting. I want to work with functions which make sense with respect to epsilon derivatives. There are two ways to understand that. The first way is to understand semi-classical Sobolev spaces. Okay, so I'll say a function u is in this. If, of course, I mean, I take epsilon derivatives to the order alpha, and I take the L2 norm, and I take the sum of that. This is fine. As a definition, again, I mean, if u is not oscillating, that's true, but it's not interesting. Okay? What I'm saying here is that u should have this kind of a behavior, but of course, maybe not linear. It doesn't have to be something more complicated. So what it could be, that's the last thing I want to say about this general notion, is I'm going to assume during the whole thing that my initial data and therefore the solution. So therefore, the solution is because I'm in this framework here, is microlocalized, epsilon microlocalized. So I'll forget the epsilon very quickly. So I'll give you the definition, and then I'll try to explain what it means. So the definition looks a lot like that quantization up there. So I'll say it's microlocalized in some compact set K. K lives in what? Well, it lives in the cotangent space to R2, right? Because my functions, I want them to be oscillating. I want to know what it looks like in x and in psi. So if you like, it's R4 here. I'm in 2D, 2 space variables, 2 psi variables. Okay, psi 1, psi 2. So K is a compact set in R4 if, for any point, so I'll write the definition and then I'll try to explain, which is not in K. So I have my K here in phase space. Okay, I have a point here outside K. I take a function which is equal to 1 near this point, and also compactly supported in outside K, so my function here lives somewhere there. Then I can compute whatever I wrote up there. So what I look like, I look for this sort of Fourier transform. Since I'm epsilon oscillating, I should put this scaling here, but I have to believe that. And I put chi of y xi, xi, u of y, dy dxi. So this is u, a function u. And this has to be what we'll say like epsilon to the infinity, meaning epsilon n for any n. Okay, so of course this makes no sense if you've never seen it before, so maybe we should see an example. Okay, so my favorite example is just a wave packet. You take a function which is a Gaussian, and then you oscillate in some way. Okay, look at this, for instance. Okay, so it's like a Gaussian here, and this oscillation. This thing is microlocalized near in x it will be q, and in psi it will be pi. I'll just stick this formula in here and apply stationary phase theorem. Right, the phase, I replace u by this, u y. The phase is what? It's I, forget about the epsilons. Epsilons are everywhere anyway. Now, okay, then you have plus I minus q t minus 1 minus p q squared. That's the phase I get if I put this u in my interval, right? Now, stationary phase tells you if this phase is not stationary, meaning if the gradient is not 0, then I can integrate by parts as much as I want, and every time I integrate, I gain the power of epsilon. Okay. So I just want to compute the phase. So I take the derivative of this phase in y, and I get what? I get minus, the imaginary part is minus psi plus p, and the real part is y minus q. Okay? So the phase is only stationary if psi is equal to p and y is equal to q, right? But my function here, my smooth function here, is microlocalized away from those points. Okay? So that means away from those points, the phase is not stationary. I can integrate by parts and the things are very small. Okay, so if you don't like this formula, which I can understand, then you can just imagine this is typically my initial date. Okay, so you're localized in phase-phase to a degree epsilon. So why is that interesting? Because you have lots of theorems.
Sorry, I'm confused with
Yeah.
the commutator. Why you don't get a net extra epsilon if you said the commutator is small, and now you make again a derivative. Doesn't another 1 over epsilon jumps out of the derivative?
You mean when I'm doing this stationary phase?
No, you have this commutator.
Yes.
So it's epsilon times the derivative of f. Ah, no, it's f. Okay.
F prime.
Hmm?
Yes, F. Yeah. Okay. So now let me go back to my problem. Okay, I have a problem because this is a matrix, right? It's not a scalar operator. So I have to take a quantization, write this as a symbol. But it's not so easy, right? The first thing I want to do is just say, every time I have an epsilon derivative, I just replace it by psi. Okay, so let's do that. And of course, I want a principal symbol, so I want something of order 1 in epsilon. So everything which has an epsilon in front of it will just go away. So the principal symbol of my matrix is just this. This I can find eigenvalues for easily. I get 2 eigenvalues, 3 eigenvalues, 0, plus or minus I square root of, psi 1 squared, plus psi 2 squared, plus 2 squared. Right. Incidentally, for people who've seen the equatorial beta plane model, when B is x, x2, this is the harmonic oscillator. Right? And that's why you have those Hermite functions coming out. The quantization of the harmonic oscillator. Well, similar harmonic oscillator. Anyway, so I get those 2 eigenvalues. Those are exactly what you call Poincaré eigenvalues. Because if I bring them back to an operator, I get the usual operator you expect me to do this analysis. But I have the 0 here. That's not very good because a 0 for a principal symbol means I have a sub-symbol somewhere. I have something of order epsilon. And it's not so easy to catch sub-symbols. People have seen that before. But there is a way, so that's a very general theorem I can tell you about if you're interested someday. When you have any matrix, a Hermitian matrix of semi-classical operators, there's a way to compute to diagonalize it totally. There's a way to write A up to some unitary operators as a diagonal operator, up to as small as you want terms. I can diagonalize this thing. This is diagonal, so it's d0 plus epsilon d1 plus etc. And you have explicit formula for each of these things. So this I'm telling you I can't prove because it takes some time. You can do it by normal forms. There are usual methods to do that. D0 will be exactly the operator obtained by taking the operator associated with those eigenvalues. Right, so it will be 0 plus or minus the integral plus square root minus square root and 0 everywhere. And A1, the principal symbol of D1, I can compute. And what I find for its eigenvalues are the Rossby eigenvalues, which maybe you've seen before, B prime C1 over something plus U bar dot psi. You see this U bar dot psi was on the diagonal before. It should have appeared as an eigenvalue, except it had an epsilon in front. So it appeared at the sub-symbol level. Okay. There should be I's everywhere, I guess. Right, so now we're pretty happy because we can prove a theorem, which I won't do, which tells you that you can replace this equation here, well, this system, by 3 equations. Right? And each equation involves some semi-classical pseudo-differential operator whose symbol I know precisely. Okay, so now I'm ready to do some analysis. I'm ready to try to prove trapping of Rossby waves. Yes.
Wouldn't that all follow epsilon to infinity?
Yeah, that means, what do I mean by that?
Yeah.
That means Cn epsilon n for any n.
And with that epsilon comes from anything but a naught, right? So if you
It comes from 2 things. It comes from the fact that I have a matrix. So even if my matrix didn't have any epsilon here, I would have lots of lower order terms because the matrices don't commute. Right? So I would have anyway an expansion. Now, on top of that, my matrix is not totally exactly pseudo-differential. I have errors, and those also contribute to lower order terms. Right. This 0 can't be exactly 0.
and
It's not a kernel.
the d sub epsilon, right? That's also depending on epsilon.
Yeah, exactly like this. I mean, this is a big mess. I have no idea what it looks like. But before any time I stop, I know exactly what those matrices are. They're all diagonal matrices, and I can compute every symbol on the diagonal.
Not the leading order is coming from a naught.
The leading order is this one. The next order will have the Rossby weights in it, and then I can go on and on. The next order is the mistake I've made here, actually. Yeah, well, the next order is just, this is not a real 0. It's an epsilon.
Oh.
Okay, so maybe I'll tell you 2 things now. So I have those Poincaré operators. I have 2 of them, and I have 1 Rossby operator. Maybe I won't give you too many computations, but I'd like to give you a flavor of what you can do on those things. Because now, from my system, I've produced 3 equations. Right? 2 Poincaré equations, which look like this: epsilon squared dt phi, let's say, plus some operator. I call it a Poincaré operator, phi equal to 0, phi plus or minus. That's 2 equations, and then I have another equation, epsilon dt phi, plus the Rossby operator phi equal to 0. Both are skew symmetric, but those are equations now. Okay. Now the question we were addressing was, can we prove Rossby waves are trapped? And the reason for all our scalings was to end up with this. So this, of course, is semi-classical, right? Again. So it's a function of x and epsilon d. The same for this one. And this is the perfect framework to study propagation of waves. Right? If you know a bit of semi-classical analysis, if not, you have to believe me, that if your initial data phi 0 is microlocalized in some compact set k, then you can prove that phi of t for any positive time, phi of t is microlocalized in the compact set k of t, which is just pushing k by the Hamiltonian flow associated with R. Meaning that you just have to solve x dot equal to minus grading psi of my Poincaré, my Rossby symbol. Psi dot is grading x r. Right? If you solve this, which you can do, everything is totally explicit. If you solve this, you know your solution will be exactly microlocalized on that compact set. That's a theorem. It's a well-known theorem. Okay. So to answer the question, well, what we were wondering in Rossby's book, in Podolsky's book, all we had to do was study those trajectories. case, I won't do it because it's a bit complicated. I need to take derivatives of this crazy thing. But you can prove it's true. You can prove that for initial data, for some, some k's, then for your initial data is in k, Rossby, those Rossby waves will be trapped. Actually, will all converge to a point where this thing vanishes. Okay, so that's done. It's understood, and it's really because we place ourselves in this semi-classical framework. Everything reduces to this ODE. That's nice. Now, what about Poincaré waves? If they're there, right? What happens to them? Well, the thing is, you can't use the same analysis for Poincaré waves because the time scale of Poincaré waves is very different. Right? It's epsilon squared. That's because Rossby waves are subsymbols. So Poincaré waves are much, they disperse differently. They have a longer time scale. So if I want to use this kind of a theorem, it will only be true on this time scale for a time of order epsilon. Right? I have to dilate the time if I want to use this kind of a theorem. So I can't use this result. Because it's known that this is only true for finite time, but afterwards anything can happen, depending on the problem you're looking at. It's not true that for longer times, depending on epsilon, your solution remains much localized. Anything can happen, depending on your problem. So I'll just finish by showing you something I learned at the time, which I found really very nice, which are called Moore estimates. And I'll finish with that. So I want to study dispersion of Poincaré waves in my setting here. So remember in the first talk I explained a little bit about dispersion, saying if you have a Fourier transform, it's easy. You just write down your solution and do a stationary phase and hope something happens. Now the thing is, my Poincaré here, I can't write a Fourier transform. I only have its principal symbol. I don't have anything else. I don't have the full expansion because there are always errors. So I can't write down an explicit estimate. I have to do something else. And something else is called a Moore estimate, which goes as follows. Actually, what I'm going to do, so I have time here. I have, let's look at x1, for instance. I'm going to prove that in the x1 direction, which is the longitude, Poincaré waves disperse and go to infinity. They're not trapped in the x1 direction. That's what I'm going to prove. So I'm going to try to draw x1. So x1 means I have my initial data to this problem here, which is micro-localized somewhere, I'm not sure where. Okay, so some region, compact region in space, in particular in x1. Okay, so initially I'm somewhere in x1. And I want to know where this goes in very large times, because I want to go to 1 over epsilon squared. I can't use this again. Okay, this is not long enough. I can use it for small time. I can use this for a time of the order epsilon. Right? If I rescale this, that's epsilon s. If I change this into epsilon, I can use this theorem. So for a tiny time called epsilon, I can use usual semi-classical techniques saying that x1 dot will look like minus greater than psi 1 of the Poincaré symbol. B plus or minus. Okay? This I can compute, and what I get is, okay, forget plus or minuses, and you get something like psi 1 over psi 1 squared plus psi 2 squared plus b squared. Okay? Now, what you might know also, so that's true for times of the order of epsilon. I know my x1 will live on such a curve. Now, what's nice about this curve is that you see my principal symbol here does not depend on x1, which means that psi 1 dot is equal to 0, because it's the derivative of the symbol with respect to x1. So that means that this is a constant. Okay? Then I also know that my energy surfaces, my curves here, live on the energy surfaces, right? The Hamiltonian flow. So this is also a constant. Okay? Especially x1 dot is a constant. So I know from this easy analysis that for a small time, as long as this works, x1 just goes straight out at some speed. Okay? So if I wait long enough, what's going to happen is that my x1 will exit, for instance, the support of this u bar. If I'm going to suppose this u bar is a compact support. U bar is a stationary solution I've given myself. if it's compactly supported, at some point my x1s will go away from the support of u bar. Let's put it here. So now, if there's nothing depends on x1 anymore, because I'm out of u bar. U bar is the only x1 dependent thing. So I'm pretty sure I can take, for instance, Fourier transform in x1, starting from that point, because nothing is depending on x1 anymore. But I can't use this argument, because this argument doesn't hold for large time. So I don't know what's happening after that. And I want to prove x1 goes to infinity. This is where I use Moore estimates, which tell you the following. So it's a general result. Moore says that, saying that if I have an operator A, which is, let's say, self-adjoint. Okay. If I give myself another operator, let's say B, okay, and I make all kinds of assumptions. I won't tell you about the boundedness of A and of B, one with respect to the other, that kind of stuff. Okay. Forget that. All I want to say here is I want to assume that if I take the bracket of A by B, okay, this has to be bounded from below by some constant. Okay, not always, but I want to assume that there is some interval in R, and there is a constant, positive, such that if I place myself in spectrally, I assume the spectrum of A is an I, so I project, maybe I shouldn't do that, the spectral projector of the spectrum of A onto this interval I, and I assume that there exists such a guy, such that this bracket is always larger than this theta. That's an assumption, okay? So then you have to compute. A is my A, it's my Poincaré. Maybe I should not P here. I want to find an operator B, and some region in phase space, such that if I take the commutator of P by B on that region, then I'm bounded from below by a positive number. That's an assumption. I have to find B. Well, if that is true, then if I take the propagator by P, which is what I'm interested in, for any times, whatever its size, what I do, I also project on I, and I assume that in phase space, B is larger than something, whatever. Okay. Then when I come out, B will still be larger than A plus theta, almost. Meaning that if I place myself on A minus theta prime t for any theta primes, this is very small. For all defined smaller than theta. Let me explain. If your initial data lives on the spectral side of B larger than some given A, you flow by your P. Coming out, you'll be larger than A plus something, plus theta t. Because if you're smaller, then you're very, very small in t. Let me give you an example, which is our example here, and then I'll be finished. My example is that for B, I'm going to take x1 simply. Okay, and I know how to compute commutators, right? Because, well, I didn't tell you actually. But when I did all my symbol stuff, I didn't tell you, but the commutator in the semi-classical world of P and B is always, when you take the symbol, principal symbol of that, is always the Poisson bracket of the principal symbols, which is just gradient psi p, gradient xb minus gradient xp, gradient psi p. That's a formula. There's an epsilon for it. Okay, so all I have to do, now I'm going to take for B, I'm going to take x1. So of course you have to try, you have to guess what's going to happen, but I want to take x1. I know the principal symbol of P is still somewhere, it's gone. I know it anyway, so P is psi1 squared plus psi2 squared plus B squared. So it's very easy to compute the bracket, right? What do I get? I had to take the derivative of P with respect to psi1 times 1, right? Because the derivative is just 1 here. And I did it before. It's psi1 0 over this thing which is constant. So it's a constant actually. Right? So that's exactly what I want. This thing is a constant. So if I choose any interval here in phase space, what I want, I get something like that because it's a constant. I just choose what I want. Okay? So this is telling me that if initially x1 is larger than something, okay, and it is because I know I've exited the support of u bar, so I'm larger than something, then for all times, whatever times, because of this Moore estimate, I know x1 will be larger than a plus theta prime t, not quite t. Here I have a t over epsilon squared. So I have a t over epsilon squared. But then my bracket here makes me lose an epsilon. Okay, and that's totally for any time. There's no epsilons in the, no restriction on time for any time. Okay, so that's telling me that initially I came out, because of semi-classical techniques, I came out of a small boundary layer, I could say, for a small time, and then forever I have an escape velocity, minimal escape velocity. I know x1 will never come back. Okay, and that's just thanks to this. So that's really very efficient. Of course, you have to guess who's going to work, but once you've seen that kind of stuff, and, well, I guess you have to be used to it. But this is just like a propagation argument, and people have seen, I won't go too far in details, but anyway, once you've found the good operator, then everything's true. Okay, so this tells you that Poincaré waves do disperse to infinity in the longitude direction, right, forever, will never come back if you have no boundary conditions. And this, once you've done the study of the Rossby waves, tells you that Rossby waves are trapped forever as soon as time is lost. Okay, so maybe I'll stop now because maybe enough. Yeah.
You said why you need this initial phase to move away. I mean, I don't understand
That's a good
enter
question.
the argument.
Okay, that's because when how should I say this? That's because I've said here that xi1 was a constant,
Okay, so
right? But it's not totally true because all the sub-symbols depend on x1 in general. But what I'm saying here is that since the sub-symbols, everyone depends on x1 because of u bar. But once I've exited the support of u bar, I'm saying I'm replacing my operator by the proper operator p, where there would be no u bar. Then I can say that xi1 is a constant because it's not true in general. That's only true for a small time. You can't define this kind of technique globally in time.
Yeah.
So as soon as time goes beyond epsilon, this is wrong. Xi1 is not a constant, right? But since I'm out of the support of u bar, at least at that point, xi1 is a constant for some time, because I won't go into the support of u bar immediately with the continuity arguments. Then I'm saying yes, but if there was no u bar, I'd be pushing to infinity. I'd never see u bar again. So it's the same as if there was u bar, since I'm not seeing the support of u bar anyway. And what I'm saying is that this.
But why you know that you get far enough to get out of your bar?
That's thanks to this. Because this is telling you that the trajectories are straight lines for a small time.
Yeah, but why is this enough to get out? Or you're just already out from the beginning?
No, not from the beginning, but for a short time, but for any time of order epsilon, for any capital T times epsilon, if you like.
Yeah, but if you go linear up, you only go up by epsilon. So why is this enough?
Right, because this is, for any T, I can do this. Epsilon times T.
Okay.
Okay, so if I rescale everything, okay, I take S is epsilon T. Okay, I work on the variable S. S goes as far as I want. So if I'm a straight line, if I wait long enough, I'll go out. And I rescale to epsilon. That means for epsilon T large enough, I go out of the support. Right? It's important that if you rescale
Epsilon is still fixed. Okay.
Yes.
Okay.
Yes. I get T very, very far, and then I go back to epsilon. I rescale.
Your U bar is localized in longitude, right? In
Yeah.
x1.
Yeah.
Is there a solution to the equations that?
Yeah, you can get shear flows, for instance. In that case, it wouldn't even depend on x1 at all. I could say
No, but
that's a bad example, but I could say this:
sorry.
a shear flow. It
You.
doesn't depend on x1, so it's cheating, but that's an example which works.
But no, but your argument here, this graph you're talking about, it depends on x1, right? You're talking about your Poincaré is propagating away in longitude away from the influence of u, right? Yeah. So your u depends on x1, right?
Yeah, well, let's say if it, yeah, right. Okay. Yeah, well, my u is a solution. Sorry, my u is a solution to an equation like. Okay, I have problems on other terms. Given some forcing, so I can adjust
You
the
could
forcing.
put a force in, yeah, sure, okay.
I did put a forcing at the beginning.
Yeah, okay.
That's how you did it. So I can adjust things so it works.
U bar is divergence free, right?
Yeah.
Any other questions?